Now let's talk about the electromagnetic spectrum. The electromagnetic spectrum that you're used to is the visible part of the spectrum, starting with red at the longest wavelengths going to violet at the shortest wavelengths. We've got red, orange, yellow, green, blue, and violet. Newton included indigo as a color between blue and violet, but it's really just a combination of blue and violet in the same way that yellow-green is a combination of yellow and green. Really, 6 is plenty. It corresponds to the fact that we see 3 different colors with 3 different kinds of rods and then combinations of them. But that's more biology. The key point is that this is the range we can see with our eyes. Now you'll notice that the edges are kind of fuzzy. The reason for that is that our sensitivity to light doesn't immediately go to 0. It just drops off exponentially. So if we have intense enough light, we can see down here to 400 nanometers or maybe even shorter wavelengths. Similarly, with intense enough light, we can see somewhat into the wavelengths that are longer than 700 nanometers. But you'll notice down here that this spectrum of the visible spectrum is only a very small part of the entire electromagnetic spectrum. The entire electromagnetic spectrum is huge. In fact, there is no limit to it, but this is a logarithmic scale running all the way from 10 to the 8th meters, or 100 kilometers long, all the way down to 10 to the negative 16 meters, tremendously smaller than a nucleus. Those correspond to frequencies as low as 10 Hz and becoming as large as 10 to the 24 Hz. Excuse me, 10 to the 8th is 100 million meters. That's 100,000 kilometers. So that's an extremely large range. And we characterize them with different names that are overlapping and have as much to do with how they're produced as they do with the actual nature of the wave. So these very long wavelengths are called long waves or long wave radio waves because they're still considered radio waves. As we get up here to sort of mid-length, meter to several centimeter length wavelengths, they're called radio waves. These are the first kind of waves that we produced. Infrared tend to come from thermal emissions, from things about the temperature that you are. You actually glow quite a bit in the infrared. And it goes all the way up to just a little bit outside of the red end of the visible spectrum. In fact, that's what infrared means. It's beyond red. Then we have in this very narrow slit, less than a factor of 2 on this giant logarithmic scale, the visible spectrum. Just shorter than the visible, just slightly higher frequency, is the ultraviolet. Those come from similar type of electrical transitions to what we get for the visible, but of slightly higher energy. Then we get to X-rays, which tend to be caused by accelerating electrons. Those can become very short wavelength, very high frequency, and then up to gamma rays, which are basically distinguished from X-rays in that gamma rays come from nuclear reactions. There's overlap in all of these. The most energetic X-rays are more energetic than the least energetic gamma rays, and distinguishing them really doesn't make any sense at all. As I said, X-rays tend to be those created by rapidly accelerating electrons. Gamma rays tend to be those created by nuclear reactions. In here between radio waves and infrared, a lot of people will refer to microwaves. But the only real distinction between microwaves and infrared is microwaves are very short radio waves that we create by actually accelerating electrons in a wire. X-rays are from free electrons being bent quickly. So this is free electrons in a wire, not free electrons, electrons in a metal in a wire, being moved up and down, just like the radio waves we talked about at the beginning of this chapter. But they're very short wavelength, very high frequency. Infrared tend to come from thermal processes. But our shortest wavelengths and the wavelength microwaves and the longest wavelength infrared have a lot of overlap. So it's not a clear distinction. If we come down here, we can look and understand the uses of these different kinds of radio waves. The entire radio wave spectrum has different uses. Maritime and aeronautical uses in the very lowest parts. In fact, if we go to the very long waves, those are sometimes used to communicate with submarines that are submerged, because those very long wavelengths can pierce through the salt water of the ocean, whereas shorter wavelengths can't. When we get up here to slightly shorter than the maritime uses, we have the AM radio, the longest wavelength of commercial radio. Then we get more maritime, aeronautical, and mobile radio stations, short waves, things like that. Then we get into the TV channels and the FM channels in between the TV channels. 2 through 6 are here, 7 through 8 are in this region, 14 through 69 are here. And then more bandwidth that's used for maritime, aeronautical, citizens band, CB, cellular phones, and mobile radio. So this entire band of radio waves is used for different purposes. Now, why do we use it for different purposes? Because Congress made a law that said these wavelengths will be used for AM radio, these wavelengths will be used for maritime radio. They needed some way to divide it up so different people's signals weren't all overlapping. Okay, something I made a comment on, but I want to show again. This picture just shows the sensitivity of the human eye to different wavelengths of light. Notice we are most sensitive right in here between green and yellow. That tends to be the dominant color of light coming from the sun, the average color of all the different kinds of light we see. It's an important wavelength to see at. We're less sensitive in the red, less sensitive in the violet. And it falls off somewhat exponentially here. But if you have really, really intense light, you can see beyond 700 nanometers or shorter than 400 nanometers.